All right. Good morning, everybody. I hope you guys are doing better now after the winter storms that hit us last week. So I guess the exam was also postponed until this weekend. So we will spend this week preparing for the test. So have you guys had a chance to do the practice test or do some sort of a review? I know for some it could be hard because I myself encountered water and power outages last week, but how are you guys doing?
My family is doing okay, and I was able to get 100 on the practice test after several attempts.
Uh-huh. Okay, that's great. That's good to know. Yeah. And that's a good thing about having multiple attempts for exams or quizzes. You can take it as many times as you'd like. Of course, there's I think an upper limit of about 20 attempts. But yeah, if you didn't get a good score at the beginning, then try to retake the exam so you get familiar with number one, the type of questions over there, the topics, and then also you get used to the time constraint because that's, I guess, one major concern among students and even myself. I'm not a very fast math solver, so I take time to answer certain questions, right? So how about the others? Okay, good to know. So yeah, let's try to spend the week trying to get back into shape because we all had the disruption last week. So feel free to send some questions that you might have about the practice test or previous topics. But while waiting for that, I want to prioritize the last two sections in chapter 7, which is about separable differential equations, exponential growth and decay, and improper integrals. By the way, up to what is the coverage of test number 2? Will it include improper integrals too? So that we can try to pace our discussions this week. Because I just saw your calendar and it seems that in the lecture today you just did a review. So is improper integrals included in test number 2?
I I'm not quite sure because we weren't able to finish the whole review, but
Uh-huh.
I'm assuming that's gonna be a yes because she has put them on the work homework.
Okay, yeah, that sounds good. All right, so if that's the case, then let's start. By the way, I just uploaded two worksheets to my website, worksheets 5 and 6. Worksheet number 5 covers separable differential equations and exponential growth and decay. And then worksheet number 6 includes improper integrals. But basically, these are just the exercises at the end of the chapters in the textbook. I just copied everything up, and then let's try to answer some of them. But I guess what I notice about these problems or exercises is that they are a little bit easier than what we see in the quizzes and so on. So if you have more interesting questions, kindly send them to the chat so we can discuss them. Okay, let me see. Michael sent a question. It's about improper integrals. Okay, I'll go over your question, Michael, towards the end of the class, if that's okay. So, so let's start with exponential growth and decay. It might have been more than a week or a couple of weeks since you have last seen exponential growth and decay. So maybe I'll start with a quick review on that. Okay. So you might be wondering why do we have exponential growth and decay again in calculus when we are supposed to talk about integrals and some techniques of integration. The thing here is that exponential growth and decay models are the result of what we call a separable differential equation. So it's a specific example, and I guess this is a good way to start talking about separable differential equation. When we say differential equations, these are just equations that involves the derivatives. So yeah, as the name implies, if you see an equation that has derivatives in it, then That's a differential equation. I'll mention something about the separability of a differential equation later. But one thing to note is that whenever solving differential equation, we are solving for functions. So unlike when solving the usual equations we saw from algebra or even in the early calculus days that you guys had, you're looking for just numbers, right? Looking for the values of x or values of y to solve a certain equation. That's it. We're solving for a number. But when we are solving differential equations, we are looking for functions that satisfy the equation that involves the derivatives. So for instance, maybe a good starting point for differential equations is this equation. Say dp over dt equals kt for some constant k. Right? So this is a differential equation because you see here that you have the derivative here, dp over dt. Remember that can be written as p prime equals kt. So it's an equation that involves the derivative. So it's a differential equation, and what we're looking for is to solve for functions p that satisfy this equation. So here we're solving for a function p of the variable t that satisfies the equation. So we are not looking for a specific number, but we are looking for a function p with a variable t that satisfies this equation. That when we take the derivative of that function p, that's what the left-hand side says, it should be equal to a constant k times the variable t, right? In applications, this usually is the case because here, remember what dp over dt is? dp over dt is the rate at which p changes with respect to t, right? And it says here that that rate of change is equal to k times t, right? So basically here, the rate of change is equal to k times t, right? So one way to solve this is to try, or the easiest type of differential equations is the separable type, wherein we can, we can separate the variables. So here we have basically two variables, p and t in here. A differential equation is separable if we can put all those with a variable p on one side and all those with a variable t on the other. So basically, it's a literal separation of the two variables. So this is an example because I can multiply both sides by dt. So I'll have dp equals, it shouldn't be t. This should be p, sorry. To make it more interesting, let's make it kp. So basically, why do I want it to be kp? So that it would be like in our applications that the rate at which p changes is proportional to the function p itself, right? So basically, you see this in population dynamics, in compounded interest, right? Wherein the rate of change is dependent on the amount of material present at a particular time t. So basically, when you say, for instance, population, the rate at which the population changes right now would be proportional to the population at the current time, right? So this is how we model such things that changes with proportionally to the amount of material present at a particular time, right? And then as I promised, here we can try to separate the variables. I can multiply both sides by the differential dt. So I'll have I have kp dt, and then I can divide both sides by p. So the differential equation can be rewritten in this way. And this is the separated form, wherein all those with a variable p are on the left side and those without or are on the other side, or those involves the variable t would be on the other side, right? And the thing about separable differential equations, once you were able to separate the variables into the two sides of the equation, then you can simply integrate both sides. So if I integrate this, or basically maybe I should write that down here. So I'll integrate the left side. I'll also integrate the right side, okay? Now, in differentiating the left, we have the integral of dp over p. So we're integrating 1 over p with respect to the variable p, right? I hope you still remember that the derivative of that would be ln of the absolute value of p, right? Equals the right-hand side now will be integrated with respect to the variable t, right? So when you differentiate with respect, when you integrate with respect to the variable t, this will just be kt, and then I'll have the arbitrary constant c here. Or in case you're wondering, well, there should also be an arbitrary constant on the left-hand side, right? And then there's a different arbitrary constant on the left-hand side, so say C1 and C2, but I can rewrite it as this, which is a usual trick in solving differential equations. So sorry, this should be a minus C1, okay? But what do we notice about C2 minus C1? Well, negative C1 plus C2 is just another arbitrary constant because C1 and C2 are arbitrary constants. Their difference will also be an arbitrary constant. That's why when you integrate both sides of an equation, it is customary to just include one arbitrary constant to one side of the equation. Because the reason is that you will just have the sum of two arbitrary constants. It will again be another arbitrary constant. Okay. Right, I hope that's clear now. Okay, and then we're solving for p. Remember, our goal is to solve for the variable for the function p of the variable t that satisfies the equation. So here I want to solve for p, but I have an ln over here. I hope you guys still remember how to get rid of the ln. The trick is to use both sides of the equation as an exponent for the natural exponential base. So what I'll do is to raise e to either side of the equation. Okay, and then here you see e is followed by ln. So they are inverses. They are inverse functions, so they sort of cancel each other out. So we'll just have absolute value of p over here, and then here I'll have e to the kt, and then loss of exponent I'll have e to the c. Right? Okay. But one thing is, maybe let's assume that P is positive. Usually P stands for population or the amount of material present. So it's a usual restriction that P is chosen to be a positive function. So I'll just put P here. The absolute value of P is equal to P whenever P is positive. And then I'll have e to the kt here. So this is a function of t. And then e to the c. Well, c is an arbitrary constant. If you use an arbitrary constant as an exponent to e, then the result e to the c is also an arbitrary constant. So maybe let's call it p sub 0. And actually, oops, right, where p sub 0 is our e to the c, right? And now we're done. We have found the solution to our differential equation. Now to check if you have the correct function p here, you take the derivative of both sides with respect to t, you should get exactly what we had in this equation, right? You should get kp. Okay. So I leave that as an exercise to you guys, but I hope you recognize this as your model for exponential growth and decay. It's an exponential growth when k is positive, and it's exponential decay when k is negative, right? Then what does p sub 0 stands for? Do you guys remember what p sub 0 stands for? Or what does p sub 0 denote? Because insofar as the differential equation is concerned, without any context to applications, p sub 0 is just an arbitrary constant. But in the context of several applications, Maria is correct. P sub 0 stands for the initial value. Why initial value? Because if t is equal to 0, usually t is associated with a time variable. So at the time t equals 0, that means the initial time. Then if you compute for p of 0, you plug in 0 for every t that you see, you get p sub 0 e to the k times 0. That's p sub 0 e to the 0. E to the 0 is 1, so you get p sub 0. And that's why I use the notation p sub 0, because that's the value of the function at time t equals 0, right? And that's how we got this exponential growth and decay model from algebra, okay? So basically, any function that changes proportionally to the current amount of that function, then that is modeled by an exponential function like this. P of t equals p sub 0 e to the kt. Now, perhaps let's look at some examples here. Let me go up. Let me know if you have some questions on that, but let's say, okay, let's try this typical problem that arises in applications, or the most, one of the most popular application of exponential growth and decay would be population dynamics. So here, problem 28 says that in 1980, the world population was approximately 4.5 billion, and in the year 2000, it was approximately 6 billion. Assume that the world population at each time t increases at a rate proportional to the population at time t. Measure t in years after 1980. After 1980. So here, the key word here is that we are assuming that the world population at each time t increases at the rate proportional to the population at time t. So if p is the population variable, right, or the population function, then this says here that the rate of change, which is dp over dt, is proportional to the current population, which basically reminds us of the model that we started earlier. That's why I know that problem 28 should be solved as an exponential growth problem, growth or decay problem, right? So we have solved this equation earlier. So we know right away that the model for the population should be this, p sub 0 e to the kt, right? That's the model we're following. And then here, we were told that we are measuring t in years after 980. So here, 1980 will correspond to t equals 0. 1981 will correspond to t equals 1, and so on. So you see here that t equals 0 is associated with 1980. So that means our model can be rewritten with more details as p of t equals p sub 0. Remember, that's the initial value of the population. When we say initial, as per the convention in the problem, that's t equals 0, and t equals 0 is actually the year 1980. And in 1980, it was said that the population is 4.5 billion. So that means this would be 4.5 billion, or times 10 to the 9th. If I'm not mistaken, right? A billion is 10 to the 9th. So 4.5, 10 to the 9th. That's our p sub 0, e to the kt. So that's our model. Now, problem A requires us to find the growth constant, or the rate of growth, which is basically the value for k. And for that to happen, we need to have some other information. Well, if you look at the problem, it says that at the year 2000, the population was approximately 6 billion, all right? So that means at year 2000, but year 2000 corresponds to t equals 20, right? Because 2000 is 20 years after 1980. So that means the population is 6 billion. So that means p of 20 equals 6 billion. So 6 times 10 to the 9th, e to the k times 20, right? And then I'll use this info in order to get the value for k. So this is one way of looking at p of 20, right? But another way, p of 20 doesn't have this factor anymore. So because we were told that the population at year 2000, which is 20 years after 1980, is equal to 6 billion, right? So that's 6 times 10 to the 9th. But another way of looking at it is, this is p of 20, which is basically p sub 0, or actually I know what p sub 0 is. So this is 4.5 times 10 to the 9 e to the k times 20, right? So this first info here, or the first segment of the equation, is from the problem. And this is from the model, right? And then I will use this two ways of looking at the population at 20, or at t equals 20, to find a value for k, right? So basically here we can solve for k because we have constants on the middle side of the equation and on the right hand side. So we can manipulate. So basically I'll first divide both sides by 4.5 billion. So I have 6 over 4.5. But what is 4.5? 4.5 is 9 halves. Then I'll have 10 to the 9th here, all over 10 to the 9th equals e to the 20k, right? So here I'll have 6 times 2/9. The billions will cancel each other out, so we'll have e to the 20k. And then here I can cancel the 3's. So I'll have 4/3 equals e to the 20k. And then we're solving for k. So I can take the natural log of both sides. So I'll have ln of 4/3 equals ln of e to the 20k. Oops. Because that's how we free an exponent. We take the logarithm of both sides. So I'll use loss of exponent on the loss of logarithms. On the right-hand side, I can bring down the exponent in front of the ln. So I'll have 20k over here, ln of e. But ln of e is just equal to 1. So ln of 4/3 equals 20k. And so k is equal to 1 over 20 of ln of 4/3. Okay, so this would be the this is the rate of change, or this is the growth constant. So here, yeah, this is our final answer for problem A. So for exams, for quizzes, I guess you can leave your answers like this. In homeworks, I don't suggest you try to write it in decimal, because you're not allowed to use calculators in the exam. So this is a nice practice, doing things without using a calculator. So keep it as 1 over 20 ln of 4/3. Okay. Okay. Any questions so far? Okay. So let's just update our model. So the model now, the population model is P of t equals 4.5 times 10 to the 9th e to the 1 over 20 ln of 4/3 times t, right? I just plug in the value for k. So this is our growth model for the population. Okay, any questions, guys? One funny thing about this is that when I learned it back in high school, I usually I usually keep this almanac, so this yearly statistical books. I like to read them. When I learned this in high school, then I look at the almanac, and then I made a table and tried to model population for each country. I know that's kind of nerdy, but I enjoy numbers back in high school. So I was really I was really surprised, and I was amazed that I can do population prediction using that, right? So, okay. Yeah, that's my nerdy portion. But now I hope that's clear. Yeah, actually, when I was a child and I don't know about any fancy math, and being able to uh, being able to forecast what would be the population 10 years in the future is a big deal for a kid. And I felt very proud of myself that I can do it back then. All right, so yeah, everybody has their nerdy sides, and I think it's time to normalize them. Okay, so let's try problem B. So for problem B, how long will it take for the world population to reach 9 billion? So that means to double the 1980 population. So this, okay. So how many years to double the population? So we're looking for the value of t, such that P of t is twice the population in 1980. So we're looking for what would be the year. such that the population P of t is equal to twice the initial population in 1980. So my setup is this, finding t such that the population model is equal to twice of the initial population. But if I remember, we said that we denoted the initial population as P sub 0. Okay. So now what I'll do is to plug in the model here, P of t, we learned is equal to this guy. So I'll just copy that over. That's my P of t equals twice the original population, which is twice of initial population. But we know the initial population was 4.5 times 10 to the 9th. So I'll just plug that here. And basically here I'm solving for the value of t, which is an exponential equation. So what I'll do is to divide both sides by 4.5 times 10 to the 9th so that the exponential function is isolated on the left-hand side. So I'll have this. Okay. Then I'll do the division. This will just be equal to 2. And then let's solve for the value of t. But the variable t is in the exponent. So remember, the way you can get rid of, you can free an exponent is to take the natural log of both sides. Actually, any logarithm that you like, but it would be more convenient to use the natural log. So I'm putting up some extra steps here just to show you all the details, but you can skip some of these because here what I'm going to do is again apply good old familiar laws of logarithms that says any exponent inside the log can come down as a coefficient. So I'll have 1 over 20 ln of 4/3 times t times ln of e is equal to ln of 2. ln of e is just 1, so I'll have 1 over 20 ln of 4/3 times t equals ln 2. And then I can multiply by 20. I'll have this 4/3 t equals 20 ln 2. And then I'll divide both sides by ln of 4/3. So I'll have 20 ln of 2 over ln of 4/3. Number of years, whatever this value is, okay? So again, don't worry if you have your answer like this. Actually, I prefer your answers to be in this form rather than using a calculator to find the decimal representation. So let's keep it like this, okay? Right, any questions so far? I guess for some, this would be just a review of what you did in pre-calculus or in your algebra classes. But again, the reason why you have these problems here is that exponential growth and decay is an example of a separable differential equation, and actually it's a very powerful tool for you to remember. Okay. Let me see what's the other question here. Yeah, Herson, that's correct. You can also use the formula for doubling time. I guess this was yeah, as Herson said, it was given in the lecture that whenever looking for the doubling time, you always have the formula kt equals ln 2. Actually, that's exactly what we did here. Remember, this is our value for k. You have kt equals ln 2. So you could have saved a lot of some steps in the solution if you remember that formula in the lecture. Whenever solving for doubling time, it's kt equals ln 2. But the reason why you are able to do kt equals ln 2 is basically what we did here. Okay. So yeah, if it was given in the lecture, you can take advantage of that, right? So it's just that I'm bad at memorizing. I don't actually remember that kt equals ln 2 is a nice starting point for computing doubling times. But yeah, if you're good at remembering things like that, then go ahead, take advantage of it, right? Okay, let me see problem C. The world population for 2010 was reported to be about 6.9 billion. What population does the formula in A predict for the year 2010? Well, basically, if you're looking for the population in 2010, that would be what would be the corresponding t-value for 2010? The year 2010 corresponds to t equals 30, right? Because our t equals 0 is 1980. Then our formula predicts that at 2010, the population would be p of 30, which is 4.5 times 10 to the ninth, e to the our rate, which is 1 over 20, ln of 4 thirds times t, but the time we're considering here is 30. So this would be 4.5 times 10 to the ninth, e to the 1.5, that's 30 over 20, ln of 4 thirds. So that's the expected population from our model for population in 2010. And basically, let me use a calculator to find this value. This would be times e to the 1.5 times ln of 4 thirds. Yeah, this is about, actually, this is 6.9282 billion. This is just an approximation, right? So which is pretty close. Says that the year 2010, I guess the data says the population is about 6.9 billion. And actually our formula or our model is a bit close to that. It's 6.92 billion, yeah, billion persons. All right. Okay, so let's see. Any questions about population growth and decay? So do you want one more example about this topic, or should we go to the more general type of separable differential equations? Any any preference? Or this topic is quite easy for you guys? Let me see. Let me just browse. Yeah, talking about decay. Yeah, there. I think some problems here talk about decay, but the only difference is that uh, for exponential decay, you have a negative value for k. For population, for exponential growth, k is always positive. For decay, k is equal to k is a negative value. So yeah, that's the only difference. But the thing is that the formulation, the algebra that you should use are the same for them. So let's see. Usually you have some half-life of radioactive materials as usual examples for exponential decay. Let me see. They actually don't have half-life here. Okay, there we go. Problem 22. For those planning to major in chemistry. So, oops, why do I have that? Let me try again. Problem 22. There we go. Okay, copied. Okay. So this is an exponential decay problem. So it says that the half-life of radium-226 is 1620 years. When we say half-life, that's the number of years for half of a material to decay. So, and this is this usually happens for, I hope I'm right, for radioactive materials that they decay through time. So if you have, say, 1 unit or one, I don't know, how do you measure the amount of radium? So if you have X amount of radium today, in 1620 years, then only half of that amount of material that you have will remain. So this is basically an exponential decay problem because the rate at which this type of materials decay depends on the amount of material present. So yeah, but here, so having that in mind, so we know that the model here is P of t equals P sub 0 e to the kt. And we are expecting k to be negative because this is a decay problem, right? So to answer problems A and B here, because they're looking for the amount of material present 200 years ago and so on. So basically here we need to find the value for k, right? So because the model won't be complete if you don't have the value for k. So here, for us to do that, let's use the fact that the half-life of radium is 1620 years. So if you have P of 0 amount of radium today, then half of it will be gone in 1620 years. That's basically what half-life tells us, right? Then in 1620 years, only half of the original amount will remain. So putting this information into our model says that P at 1620, remember this tells us the amount of material in 1620 years would be equal to half of what we have right now, right? So basically this info is interpretation of half-life, right? And then another way of looking at P of 1620 is you plug in 1620 into our model. Use t equals 1620. So this info is from our model. So again, we answered this problem by looking at P of 1620 in two ways, right? Looking at it as the amount of time for half of the material to be present, which is basically dictated by the half-life condition, and looking at the model, plug in 1620 into our model, and you see that the last two parts of this equation gives us an equation that can be solved for k, because here we have 1/2 P0 equals P0 e to the k times 1620. We can divide both sides by P sub 0, and that would be gone. So we'll have this, okay, right? Then I take the ln of both sides because I'm looking for k, which is right up there in the exponent. So to free it up from the exponent, we take the natural log of both sides. And I guess here, if it was mentioned in the lecture, you could use the halving time as ln of 1/2 equals kt, which is basically the same thing. So you have ln of 1/2 equals 1620k ln of e, but the ln of e is just equal to 1. So k is 1 over 1620 of ln of 1/2. So therefore, our model can be updated as P of t equals initial amount e to the k, which is 1 over 1620 ln of 1/2 times the number of years, right? So this tells us what would be the amount of material t years after we have started. Okay. Now let's answer problem B. Problem A. Problem A tells us that if the current mass of the sample is 100 grams, what was the mass 200 years ago? So that means it tells us that if today, let's count today as the current time or the starting time. So if P of 0, which is P sub 0, is 100 grams, then what is the amount of material 200 years ago? So that would be P of negative 200, right? So basically that's how we can answer problem A, right? So P of negative 200 represents the amount of material that was present 200 years ago, knowing that or setting the current time as our initial time, okay? Oh, by the way, I mentioned earlier that we're expecting k to be negative. If you use a calculator, you will see that this is basically negative But without using a calculator, well, 1 over 1/620 is positive. 1/2 is a fraction. The ln of a fraction is always negative. So that's why this is negative times positive. I'm sure this is a negative number, right? So now this would be easy. The amount of material present 200 years ago is P of negative 200. Just plug in negative 200 into our model. But again, in the model, we assume that P sub 0 is 100. So I'll put the 100 there. E to the 1 over 1620 ln of 1/2 times negative 200. Okay. And definitely the answer you'll get here is something greater than 100 grams because that was 200 years ago. But that won't be double because the half-life is 1620 years, right? So whatever here, whatever number you get here would be in grams. I'll just leave it like that. Yeah. Or if you want to be fancy about it, you can write the answer as 100 e to the, well, I have 1620. I can divide, well, supposedly I'll have negative 200 over 1620. I can cancel the tens, and then I can divide by 2. So I'll have what? 10 over 81, I guess. I hope I'm doing the algebra right here. Though you're not required to do so, but... And then the negative sign can go inside the ln as an exponent, so I can write it as this ln of 2 grams. Right? I guess that's a prettier way of writing the final answer. Playing with loss of exponents and just evaluation of fractions. But I'm perfectly fine if you leave your answers like this. For one, it's easier to check your answer and trace where you, if you got it wrong, to trace where or what you did wrong. But yeah. Okay, so part B. Well, for part B, the question is how long will it take for the sample, or how long will it take for the sample to be reduced by 75%? So how long will the sample be reduced by 75%? Right? So basically here we want to find T such that the amount of material present at that time T is equal to 25% of the original amount, right? Because that's the moment when the sample was reduced by 75%, when only 25% remains, right? So now we know the model. P of T is equal to P sub 0 e to the 1 over 1620 ln of 1/2 times T equals 0.25 P sub 0. Or you can write 0.25. Maybe it's better to write it as 1/4. Okay, and then we divide both sides by P sub 0. So we have e to the 1 over 1620 ln of 1/2 times T equals 1/4. Okay, then we take the natural log of both sides. We'll have 1 over 1620 ln of 1/2 T equals ln of 1/4. I skipped some steps here, but I hope you guys recognize from the previous solutions that we had what are the steps that I skipped. But basically, this is what you get, and then we solve for T. T will just be ln of 1/4 divided by 1 over 1620 ln of 1/2, or basically you can write it as 1620 ln of 1/4 over ln of 1/2. Okay. And this is what? This is in number of years, so this is years, whatever that value is. But what do we expect here? We expected the answer would be greater than 1620 because 1620 is the number of years before half of the material will be gone. So we're looking here for the number of years when the material will just be 25% of what was present before. Okay. Okay, any questions here? No questions? All right. So I hope that those are sufficient examples for exponential growth and decay. Now let me see. Maybe let's try some problems from separable differential equations, because if I remember it right, you said that you didn't cover them in the lecture, but instead you were supposed to watch a video about separable differential equations. So I guess this would be a nice thing to look at, to try to solve them in a live class setting. So exercises 1 to 12 are differential equations. Again, you can recognize a differential equation easily because they are equations that involves the derivatives. And at least for this class, the only type of differential equations that we want to solve are those that are separable, meaning you can put the variables into two separate sides of the equation. There are more complicated differential equations, and they are the topic for more advanced math classes. So let's just stick to the basic, right? Let's see. Let's try some of them. Any problem that you think is interesting here? I only have 3 minutes here, so let's try probably a quick one, and then hopefully we'll see more complicated ones next time. So let's try. Okay, let's try problem 4. Problem 4 says y prime equals e to the x plus y. Okay. And again, to solve this, we'll try to separate the variables here. How do you separate the variables? Well, the first thing is to rewrite y prime as dy over dx. Because remember, y prime is just another notation for dy over dx. Equals here, since my goal is to separate the variables first, I'll write it as e to the x times e to the y using loss of exponents. And then now I can multiply both sides by dx. So dx will be here. E to the x will remain here, but e to the y should be on the other side. So I'll divide both sides by e to the y. So I'll have this. Okay. And this is the separated form for the differential equation, because all those with a y are on the left-hand side and those with an x are on the right-hand side. And why do we want to do that? We want to separate them so that we can solve the equation by simply integrating the separated form. So what I'm trying to do here is to integrate both sides of the equation. I'll write it as e to the negative y dy equals integral of e to the x dx. Well, for the left-hand side, I need to use u substitution here. So for the left-hand side, I will let u to be equal to negative y, then du is equal to negative dy, so that the left-hand side can be rewritten as e to the u times negative du equals the integral of e to the x dx. And then I can now integrate. This would be negative e to the u equals e to the x plus c. Remember the trick that these two sides supposedly will have their own arbitrary constant. So the left-hand side should have been negative e to the u plus a c1 equals e to the x plus c2. But again, I'll just put all those arbitrary constants on the right. So I'll have C2 minus C1. I'll just call it one big arbitrary constant C, right? Then I'll go back to the original equation, to the original variable. I'll have negative e to the minus y equals e to the x plus c. I'm not sure, but most of the times this is a acceptable final answer. I'm not sure what is the preferred form for the answer in this class, but if you want to solve for y in terms of the variable x, then what you can do is to take the natural log of both sides. But let's see. Yeah, but that will be a little bit complicated. If you want to take the natural log of both sides, you should take the absolute value of both sides. So I guess this form is acceptable for us to avoid some complications with absolute values. So as long as all the derivatives and integrals are gone, then the resulting relation that you have would be the solution to the differential equation. I'll check if you are required to rewrite this in y in terms of x. That will entail a couple of algebraic steps or restrictions. But otherwise, let's keep it like this for now. Okay, and then let's see what would be a more preferable form. Okay. All right, so I guess that's it for today. So on Wednesday, I'll try to answer a couple more problems about differential equations and then go to improper integrals. But again, don't hesitate to send in your questions if you have some questions about the practice test. Oh, I'm sorry, Michael, I forgot to talk about your problem. Perhaps let's do that. Let's start with that next time when we talk about improper integrals. All right. So any questions before we go? None? Okay, so that's it for today, guys. Thanks for coming. See you again on Wednesday, hopefully with your questions about the exam. All right. Okay, bye.